Alright, welcome to part 2 of our final exam review. Looking at number 4. Got two trains approaching each other, Thomas and Ben. Thomas leaves point A, traveling at 5 meters per second. Ben leaves point B, going at 8 meters per second. Where do they meet? Assuming they start at the same time. So remember, for these problems, we've got xf equals vt plus xi. This is really just the equation of a line when you have a position time graph, where your y-intercept is xi, the slope is velocity, your x-axis is time, and your final position is the other y point at the end. So you do that for both trains, for Thomas and for Ben. For Thomas, his velocity is 5 times t, and he starts at 0. For Ben, the velocity is 8, but in the opposite direction, so negative 8 times t. And they start 5 kilometers apart, it says in the problem, but that's 5,000 meters. Set these equations equal. You've got 5t equals negative 8t plus 5,000. Move the 8t over, you've got 13t equals 5,000. Time equals 384.6 seconds. As far as where, you can plug that t back in, either for Thomas or Ben. Either way, you get a final location of 1,923. The 1,923 meter mark. So making a graph for this, we've got our position versus time graph. We'll do this in seconds. Position in meters, and I'll just scale this up. So there it's scaled. Ben starts 5 kilometers away. Thomas starts at 0. They're going to meet at 384, 1923. 384, 1923 is about there. Both trains start at the same time. So there's our graph. For B, it says this time Thomas travels at 5 meters per second, but Ben is going to accelerate at 0.05 meters per second squared. Assuming they start at the same time, where do they meet? We'll switch to red here. So for Thomas, you got xf equals 5t plus 0. Ben, we've got acceleration now, so remember we're going to use one of our kinematic equations, which is delta x equals vit plus 1/2 at squared. And delta x is really final position minus initial position. So all we're doing is moving initial position to the other side, so you're left with xf equals vit plus 1/2 at squared plus xi. So for Ben, xf equals, he starts from rest, so 0 plus 1/2 0.05 t squared plus 5,000 for his initial position. Set these equal, you've got 5t equals negative 0.025. Sorry, I forgot to put the negative sign in the acceleration. So negative 0.025 t squared plus 5,000. So get everything on one side because you're going to have to use the quadratic equation. So I'm going to put everything on the left. 0.025 t squared plus 5t minus 5,000 equals 0. I'll do the quadratic formula. And my time is either 358 seconds or negative 558 seconds, which is not an option. As far as where, I can plug that time back into either equation. Obviously, Thomas's equation is easier, so if I do 5 times that time, that gives me the meeting location. And they're going to meet 1,792 meters away. A little bit of rounding there. C here, the last train question. Same as scenario B, but this time Thomas starts 30 seconds after Ben. So now we've just got a delay. So for Thomas's equation, final position equals 5, and we're going to do t minus 30. Take into account the fact that Thomas has 30 fewer seconds than Ben to move. Ben's equation is still the same as it was last time. xf equals 1/2 negative 0.05 t squared plus 5,000. So we end up with 5t minus 150 equals negative 0.025 t squared plus 5,000. Again, get everything on the same side of the equal sign so you can do the quadratic equation. I'm going to put everything on the left again. So that's 0.025 t squared plus 5t minus 5,150. Do the quadratic formula. Time comes out to 364.8. The other answer is negative 565, but obviously that can't be right. Plug that time back in. So 5 times 364.8 minus 30 gives us a final position of where these two would meet at 1674 meters. And that's from where A started. That's from where Thomas started. On to number 5. If the force of static friction on the box is 25 newtons, what's the maximum applied force that will not result in motion? So not result in motion means we're going to stay in equilibrium. So finishing the diagram here, we've got an applied force up and to the right that we're trying to figure out. It obviously has an x and a y component. We've got force of gravity down, that's going to be 5 times 9.8 or 49 newtons. We've got a normal force pulling up. It's not going to be as strong as force of gravity because we have a y component of our pulling up. So the normal force does not need to be as big as the force of gravity. And we've got this force of static friction that's going to be the same as the x component of our applied force. It has to be because they're the only x forces and we're in equilibrium. So that means if this force of static friction is 25 newtons, that tells us the x component of our applied force is 25 newtons, which should help us find the hypotenuse because we have the adjacent side and the angle. So cosine of 15 equals 25 over force applied. So force applied equals 25 over cosine 15, which is 25.88. We're then also asked to find the normal force. So we can find our y component of the applied force pretty quickly. That y component, we can use tangent, I guess. So tangent 15 equals FAY over 25. That's going to give us a y component of 6.7 newtons. And so Fn plus that 6.7 are balancing out the 49 newtons going down. So we can just subtract from 49 and get 42.3. Next problem, we've got a car on an inclined plane. We're going to make and label a free body diagram for the car. So I'll just do it off to the right over here. You've obviously got force of gravity going down. You've got your normal force perpendicular to the ground. It's not moving, so there's force of friction up the hill, static. And essentially that's what it is, but we know that we're going to have to break this normal force, or sorry, this force of gravity into its two components. So we might as well do that now. FGY, FGX. And we'll label some things as being the same. Alright, B wants pairs of forces that are the same. That's Fn and FGY, as well as Fs and FGX. Part C wants to know the force of static friction on the car. So I'm just going to kind of blow up the force of gravity on the car. We know the force of gravity on the car because we can multiply the 1,200 kilograms by 9.8. Fg equals 1,200 times 9.8. So that's 11760 newtons. And so the force of friction is going to be equal to Fgx. So if we can find Fgx, we've got our force of friction. So that's opposite the angle. So sine 35 equals Fgx over 11760. Fgx equals 6745 newtons. And I would label that as uphill for the force of friction. And I'm almost to the limit for how long this video can be, so I'm going to pause there and I'll make one more video hopefully to finish this up.